the work that we've been doing on automated cohort retrieval for EEG medical records. As we all know, there's vast amounts of electronic medical information out there, but leveraging this into useful things is a lot more difficult than people make it out to be. And I'd like to introduce you to some of the challenges in doing that with respect to EEGs. At Temple, we've been focused for quite a while now on building a very, very large archive of EEG data. I'll tell you about that in a moment. And that really forms the basis for what we're trying to do to show that you can query both text and signal information and build useful tools out of this kind of a resource. What makes this a very challenging problem is that automatic interpretation of EEGs is a very difficult thing. We've worked for many years in areas like speech recognition and a little bit on image recognition. These are much more straightforward in many ways, but EEG interpretation is actually quite difficult, and I'll tell you a little bit about that today as well. But we have developed a cohort retrieval system. We will demo this tomorrow during, I think, from 12 to 2 during the poster session. But this is a system that allows you to do structured and unstructured queries on this data. And all of this is available as open source. We've done almost everything in open source for quite a long time. So, what is the system? Well, the system looks something like this. Queries can be submitted that allow you to search both signal data and report data. There's a simple query building interface that's supported. You can build some structured queries here, or you can type unstructured queries as well. The search results are displayed in a way that links the records that match your queries, in this case EEG signals data and EEG reports, and it shows you these in a ranked way so that you can look at the top ranked candidates and things like that. The user interface was developed with a lot of feedback from neurologists that we work closely with. We have a pretty large working group of neurologists, and we've been trying to make sure that everything we do is relevant to their work. The system has two main components. There's a system that processes the EEG signal data and produces event information. This identifies temporal and spatial locations of signal events like spikes and seizures and things like that. 2 levels of deep learning are used in this system. We've done a lot of work over the past couple years in applying deep learning techniques to this problem, and I'll tell you a little bit more about that in a moment. The second component of the system is a natural language processing system called Mercury, and this essentially does similar types of analysis on the text data, looks for temporal relationships, looks for domain information. We have a large inventory of medical concepts and such, and it essentially parses these reports and produces concepts and information that can be queried. But the core of this is a very, very large database of EEG data that we've been building for quite a while now. There's currently over 30,000 sessions in this data, over 16,000 patients. We've been building this now since 2000. Well, the reports go back to 2002. We've been building this now for about 6 years. We continue to build it. There's several components to this database that are of use to people. We have a very large manually annotated portion of this for seizures. That's what we call the seizure detection database. We have other data, things like normal, abnormal, and some raw EEG events. And the database continues to grow at a rate of about 3,000 sessions per year. We've also incorporated data from other sites into this database. And this is going to be the subject of a Kaggle-style challenge that we're collaborating with IBM on. That challenge will probably be released in the fall, and we're hoping to have a pretty large number of people try to compete in this problem. The specific problem will be seizure detection, but it'll be based on this data. We have the data structured now into training and development tests. We also have a blind evaluation set, and we've also annotated data from Duke University that will be used as an evaluation set as well. So it's a very large, very substantial body of data, probably the largest data set of this type in the world. It's available open source. You just go to our webpage, sign up, and you'll get the password to reach the data. So if you're interested in this kind of thing, we can talk offline more about it. In terms of, so what makes this difficult? Well, Seizure detection is, or interpreting EEGs is quite an art. But neurologists train fairly extensively. It usually requires 3 or 4 years of post-medical school training before you can actually interpret these EEGs. Doing high-performance event detection on these signals is very difficult because the signals are very noisy, and it's very subtle the ways in which they determine events of interest versus just noise. The way we present the data in the demo and the way we generally work on this data has been structured very heavily around the way pathologists are used to looking at the data. Neurologists. They're very specific about the way they like to look at these signals and the way they interpret them. So believe it or not, they're still using a technique that's very similar to the way they used to look at these things on paper. So you have to kind of work within their framework if you want to speak their language and get information from them. So we present the data in a way that's very similar to the way they currently annotate these signals. And within that framework, then, we have both manually and automatically labeled data. The entire corpus now has been automatically labeled using our best technology. So how do we do this? Well, from the signal side, when we process EEGs, we work with a system that uses essentially 3 levels of processing. We have a low-level deep learning-based processor, first pass, that uses convolutional neural networks and tries to essentially reduce the image to a set of candidate events for things like seizures. We follow that with a second level of processing where we try to incorporate spatial and temporal context into the system. We follow that with a third level of processing, which is based on some of our experience in other domains like speech, where we do a statistical language model to try to smooth out some of the incorrectly detected events. It was mentioned earlier how wonderful deep learning is. As we all know, deep learning is hot. Sensitivity on this task is about 35% at a false alarm rate of about 7 per 24 hours. That's very good. We've gotten pretty good at this, but that's still a bit away from clinical accuracy. The neurologist would like sensitivity to be at 75% at a false alarm rate of 1 per 24 hours. Maintaining a false alarm rate of 1 per 24 hours is very difficult. And we've worked quite hard to reduce the false alarm rate over the past few years. And we're using state-of-the-art machine learning. We've tried just about every algorithm that's been published easily, and we're pretty knowledgeable about how all these different algorithms perform on this particular task. So this is not something where you just drop in the latest and greatest code from TensorFlow or whatever and get good performance on this. This is quite a challenging problem even for state-of-the-art machine learning. And therefore, the data becomes very important. We need a lot of data to get these algorithms to converge and to perform well. And that's why we've spent a lot of time building this large data resource, because without that large amount of data, you just can't get these algorithms to do useful things. On the NLP side, we use a fairly sophisticated NLP processing system. This is developed by our colleagues at University of Texas at Dallas, who are collaborators on this project. And this system essentially uses deep learning to parse these reports and spot medical concepts and relate those medical concepts. And it uses an extensive amount of domain knowledge, which we collect from various sources. We are able to identify a number of different types of events in these reports. Again, the key thing is we need both spatial context, what topics are appearing within the reports, how they're related to one another, and also temporal context, how a patient has been progressing. One of the nice things about this database is we have patients that have had multiple EEGs taken, so we can actually follow the medical history of a patient over time. And the NLP system tries to also do that kind of modeling as well. One of the major outcomes from this project is indexing of all this information. So in addition to providing the raw data and such, we're also providing the index, and hopefully we'll be able to upload that into some of the other data resources you're hearing about at today's conference as soon as they're able to absorb this kind of information. It's a pretty large repository of relationships. But all this then goes together, and it all is queryable so that you can run queries to discover relationships between data. The precision and recall on the report processing side are pretty good. We're typically operating above 0.5 on these kinds of things, and in some cases can get accuracies in the, up into the F ratios of above 0.8 or so. So I think we're doing pretty well on the text processing side. The signal processing side remains to be a bit of a challenge. And as I mentioned, a major outcome from this is going to be the index of these relationships and such. So big data resources are really critical to this kind of research. And again, despite hearing about all the wonderful things about deep learning, I've got my clock here, it's very difficult to get algorithms to converge on this data unless you're very careful about how you do your deep learning. So this is a really good playground for sorting out what works and what doesn't work with state-of-the-art deep learning algorithms. The ability to search both signal data and text data is really important. The signal data is very noisy, and the hypotheses you get from the deep learning systems aren't very noisy. So it's important to be able to integrate both of this information. The future work, we're expanding the database at the rate of about 3,000 sessions per year. We're also manually annotating a large portion of this data for seizures. And we have other automatically generated annotations that we're also releasing as part of the corpus. And I wanted to sort of advertise this upcoming Kaggle-like challenge that IBM will be announcing shortly, where we're going to focus on seizure detection on this data. So this is a little bit about our project. This will be going on for the next few years, and we think we're making a lot of good progress on EEG interpretation. Thank you.
1 minute for questions. Okay. Does anybody have any questions? Okay. If no, that's okay. There's one question. You just speak louder.
Is there any competition between the algorithm and the neurologist in terms of detecting seizure using EEG, and who is more accurate? And
The algorithms, like I said, perform at about 35% sensitivity at about 7 false alarms per 24 hours. Neurologists, the ones who can do this well, probably perform above 75% sensitivity at below 1 false alarm per 24 hours. So the false alarm number is the real thing. The sensitivity we can move around quite a bit, but the false alarm number is what's really important to them. If the false alarm rate gets above 1 per 24 hours, they will tell you the system will not be clinically relevant because they're spending too many time looking at false alarm data. But the way neurologists interpret these, that's a whole nother topic of discussion. We can talk offline about that. Some neurologists are not as good at this as they think they are. They generally look for the major things, but they miss a lot of the details because they have to go through this data really, really fast. Some neurologists will actually, when they do this in the clinic, they'll have 3 sessions going in real time. They'll be scrolling through 3 sessions on 3 terminals at one time because they're pressed for time, and time is money and all that wonderful stuff.